So let's consider some other variations of the coloring. So in the normal, normal coloring, there are some patterns that we forbid. For example, to adjacent graph vertices with the same color is forbidden in the chromatic number. And then other chromatic number before, this can be characterized with the what we forbid. For example, the S sub R minus 1 coloring forbids a structure that there are graphs with the same color, and there are at least R such vertices with the same color and one vertex. We forbid this, then that's exactly S sub R minus 1 coloring. And there are, we can also forbid other structure. We say on a cyclic coloring is a proper coloring with the additional constraint. Some other things are forbidden, where every cycle receives at least 3 colors. So in other words, the union of 2 color class induces a forest. So it doesn't contain any cycle. If you take the union of 2 color class, then you don't see any cycle. So it is a forest. And also, let's say a star coloring is a proper coloring where each 4 vertex path receives at least 3 colors. So in other words, you don't see any 4 vertex paths if you take a union of 2 color class, which means any union of 2 color class induces a star forest. Star forest is a disjoint union of star. A forest which is disjoint union of star. Each component of the forest is a star. And we say the cyclic chromatic number say KAIST of A, G, and the star chromatic number KAIST of S, G are the minimum K such that G has a cyclic K coloring or and star K coloring. So this denotes the smallest K such that G has a cyclic K coloring, and this denotes the smallest K such that G have a star K coloring. It's kind of trivial that star forest is a forest. So we have that if we have a star coloring, then that trivially is acyclic K coloring, acyclic coloring, but the other way doesn't hold. So these inequalities are trivial. Then again, the natural question is that, say, for each of them, can we prove some bounds in terms of other graph parameters? I mean, the first thing we can think of is maximum degree. Kostochka and Stoker, 2012, proved that this acyclic chromatic number is always m-1 plus maximum degree plus 1 square over 4 and take the floor. And how can we prove this? So in order to prove this, we need to specify what we should forbid. So here we should forbid two-colored cycle. So all cycle we don't really care because it anyway, if it is proper coloring, it anyway, contains at least 3 colors. But we don't want any of this two-colored even cycle. Then if we want to say color one vertex by one vertex, then you don't want a situation that at the end you are ending up having this picture, and then now you have to color this, and then somehow you use this green. Then this is the situation that you want to avoid. As long as you don't have this situation, then you never end up having a two-colored cycle. So this kind of shows you that the dangerous situation is when there is one vertex not colored and two of its neighbors have the same color. If we can avoid this situation, then we will never get a cycle with two colors. From that, we can come up with some algorithm which colors one vertex by one vertex and then finishes on acyclic coloring. So let's prove this upper bound by presenting the algorithm. Let delta be the maximum degree, and we color the vertices one by one. And we call partial coloring of G, say, suitable if no adjacent vertices have the same color and no uncolored vertex has two neighbors colored with the same color. So we don't have this situation, and no cycle is two-colored. And this is some suitable. We define this as suitable. Any partial coloring satisfies this is suitable. In particular, empty coloring is suitable. If we don't color any vertices, then it's trivially, no two adjacent vertices have the same color, and no uncolored vertices has two, colored neighbor with the same color, and no cycle is two colored. And now we want to extend the empty coloring one by one. So assume we are given partial coloring, which is suitable. And we choose one vertex which we will color at this time. And we choose X, vertex that we want to color in a special way. Not just any vertex, it's uncolored vertex, of course. But it has the most number of colored neighbor. All the uncolored vertex, we can count the neighbors of this, which is colored. And we count that for all uncolored vertices, and we choose the one which has the largest number of uncolored neighbor. So if X has J uncolored neighbor, then what happened? We have this X, and it has J colored neighbor and some uncolored neighbor. And now what's the dangerous situation? Dangerous situation is that now we want to give the color here to X. But if this is a green, then we don't want to give green here. In that case, we have this one uncolored vertex with the same color. Same colored neighbor. So we want to avoid these colors. So altogether here, we want to avoid these colors and these colors. And we want to minimize the number of colors here that we want to avoid. That motivates this choice. Because if X has J uncolored neighbor here, then by the choice of X, each uncolored neighbor of X also has at most J uncolored neighbor. J colored neighbor, sorry, this is also colored neighbor. So if X has J colored neighbor, then each of these vertices also has at most J colored neighbors. And since how many uncolored vertices are there around X? Since there are at most, the degree of X is at most delta, so there are at most delta minus J uncolored neighbors of X. The number of colors we need to avoid is at most we avoid this J colors here, J, and then for each of this delta minus J color we have to avoid J again. So this is J times delta minus J, which is, we know that J and delta minus J sum up to delta. So this is at most 1 plus delta minus 1 square over 4. This is simple calculation. So this is maximized when both of them are delta over 2. Then you can prove this. Hence, what do we know? Wait, did I do the correct calculation? Give me a moment to just check some calculations. One less. So we have to avoid one less colors than the number of colors that we have. Hence, there is always a color that can be used for X to obtain a new suitable coloring. Because we color this with completely new color, which doesn't, which is different from all of this color. So what do we get? We still have no two adjacent vertices have the same color, and no uncolored vertices has two neighbors colored with the same color. And this, in particular, so this, before we actually color this X, it was uncolored vertex. And because it was suitable coloring, which means that there was no two vertex with the same color, which is neighbor of X. So even if we finish the coloring here, there is no way that we get a two colored. There is no way that we complete two colored cycle. So in the new coloring, we still have no cycles. It's two colors. So we can extend the suitable coloring, and we can repeat this until we get a desired acyclic coloring of G. So here we have the quadratic upper bound in terms of the maximum degree. But is it best possible? In fact, it is not best we can do. So, Alon McDiarmid Reed in 1991 proved that this acyclic chromatic number of G is at most, say, 50 times the maximum degree to the 4/3. So, they use probability method to prove this. They actually use the robust local lemma, and you are given a graph, and then you define some bad events, which gives us the structure that we want to avoid. And then we randomly color the vertices, and then, define bad events that as we get a undesirable structure, substructure. And then they show using local lemma, they show that with positive probability, you can actually avoid all the bad configurations so that the resulting coloring is what you want. So with positive probability, you get a good coloring, meaning that there exists a good coloring. And which is a bit lengthy, so we will not prove this. But also we can ask that how good this bound is, and that we can actually want to prove it here. So same people, in the same paper, they prove that this is close to best possible by showing that there exist graphs with maximum degree delta and acyclic chromatic number at least some constant times delta to the 4/3 over log delta to the 1/3. So up to log term, it shows that up to log term and constant, it shows that this upper bound is almost, close to tight. So how do we prove this? Basically, we want to prove this by using probability method. We generate a random graph, and then we show that with positive probability, the resulting graph has a cyclic chromatic number bigger than this. So given a vertex set, bracket n. So in case, for the people who has not taken the undergraduate graph theory last year, might want to look at the lecture note on the internet. It has a chapter regarding the probability method and random graph. And taking a look at it might help you to be familiar with this kind of argument. So what you do is we generate a graph G at random by letting each vertex pair to be on edge with probability P independently, where say P is 3 times say log n over n to the 1/3. So which means that we have n vertices, which is 1, 2, 3, 4 to n. For each 2 vertices, which pair, we flip a coin, which comes up with head with probability p, and then tail as a probability 1 minus p. If it is head, then we add an edge. And if between 2, if it is not an head, then we don't add an edge. We do that for all n choose 2 pairs. And then those, coins are fair coin and then independent coin. So whatever we have, the result we have here does not affect the probability of getting heads on elsewhere. And let E be the event that a cyclic chromatic number of resulting graph is smaller than n over 2. Then what we do is we show that this tends to 0. This tends to 0 as n increase, as n goes to infinity. So our claim is that for any fixed partition P of these vertices into at most n over 2 parts, n over 2 color classes, the probability that P is a cyclic coloring of G is at most 1 minus P to the 4 to the n over 4 choose 2. So that's our claim. Let's write it as a claim. So before proving this claim, let's show that this is actually enough. So how do we do it? We randomly generate the graph on the vertex set. And then, but before even generating G, we could consider all the possible partitions, which is possible coloring. And once we have G, we can check whether, this coloring works for G, and whether this coloring works for G, this coloring works for G. If all coloring fails to work for G, that means, there is no way to color G with at most n over 2 colors. So that automatically shows that this is strictly bigger than n over 2. if, we already take the all possible colorings, and then if none of them works, then we are done. For that, what we do is we compute the probability. So G is not fixed yet. So we compute the probability that this does not hold or does hold. So in this case, we want to bound the probability that it holds. This is at most this. And this works with probability that, and this works with probability that, this works with the probability that. And the probability that at least one of them works, we can actually find an upper bound. And then if that upper bound is smaller than 1, then, or if that upper bound goes to 0 as n increase, then the probability that G has a secret Fibonacci number, at least this number, goes to 1. So the probability, if we write a bit more formally, the probability that the event E holds, which is the probability that this resulting graph has a secret chromatin number at most n over 2. This is summation of, let's say, all partition P. The probability that P is on a cyclic coloring for G. So there is one step here, that the probability that at least one of P, at least one P among this partition is on a cyclic coloring of G. And then this as a union bound. If you have some event and you take the union, the probability is at most probability of first event plus probability of the second event. And there are finitely many partitions, and then you take the union bound. So this is union of the events that the P1 is a cyclic coloring, and the event that P2 is a cyclic coloring, and so on. You take the union, then that's exactly this. And if the claim is proved, then what's this? This is P. You sum over P, and then this is n over 4 over choose 2. And then how many partitions are there? There are at most n to the n partitions. This is trivial bound. You just put at most n parts, and then from 1, 2, 3, this vertex you put into one of them. You choose n choice. Here you choose one of the parts which has n choice, which has n choice, which has n choice, and so on. At the end, some part is empty, and you discard. Then this shows that the number of ways to partition this is at most n to the n. And this is what we have. And with some equality, we know that this is at most e to the negative 4, p to the 4 times n over 4 choose 2. And this is e to the n log n minus n over 4, 2 times 3 to the 4 log n over n. And 16, 32, so 32, so this is roughly this minus n squared over 32, and then you divide this n times 3 to the 4 log n is smaller than e to the minus n log n, which goes to 0. So to show that this graph has a cyclic chromatic number less than n over 2 with high probability, with the probability which is close to 1, it suffices to prove this claim. And let's prove that claim. So let P be the collection P1, P2, P, say, R. And R is at most n over 2. And if some chiral class has a size odd, then we just delete one vertex. Discard one vertex from each class of odd size. As R is at most R over 2, we still obtain at least n over 2 vertices in even-sized parts. So if we have some parts which has 3, 2, 5, 6, then we simply delete one and delete one here. And number of vertices we delete is at most R, which is at most R n over 2. So we still have n over 2 vertices here, at least n over 2 vertices here. And now we further partition them. To get disjoint pairs U1 to US with S1 over 4 such that two vertices in each pair lie in the same original pair, which means that if there are only two, okay, these two are pair, U1, U2, and here you have more than two vertices, so you partition into pairs, and then here again U5, U6, U7, you partition them. Then that's U1 to US, and you know the S is at least n over 4, because at least n over 2 vertices are here, and you pair them. And what do we know? If 4 edges, so you have UI and UJ, and if all four edges are here, are all edges, if the 4 edges between two such pairs, so remember that we are generating random graph G, and we decide by tossing a coin. If we toss the coin 4 times and 4 of them are all head, so we get all 4 edges. Then the 4th cycle is either monochromatic if, both of these UI and UJ comes from the same part here, or two-colored. Even if one part comes from here and the other part comes from here, this is two-colored with this coloring P. In either case, the coloring is not acyclic. And to avoid this on how many pairs are there? N over n choose 4, choose 2. S choose 2 is, at least n choose 4 over 2. So if there are, say, U1, U2, U3, U4, what happens here and what happens here and what happens here are all independent. So all these pairs are, independent event. So to avoid this on all pairs, then each one of them, we have to have the probability that this holds. So all 4 of them are there with probability p to the 4. The probability that this doesn't happen is 1 minus p to the 4. And then all pairs, this has to hold. Those are independent events, so you just multiply. So we may stay outside of the independent events that have probability p to the 4. So we conclude that the probability that p is on a cyclic coloring of G is at most this. So note that, even if we avoided this situation, that doesn't necessarily mean it is a cyclic coloring. But once one of them happens, it is sure that it is not a cyclic coloring. So this is a necessary condition, so it provides an upper bound on the probability. And now we conclude that, with high probability, so say with probability at least 0.99, we have a cyclic trigonometric number at most n over 2. But what's the maximum degree? Then each vertex V has a potential, n-1 potential neighbors, and each of them is a neighbor with probability P. Then expected degree of a vertex is actually n-1 times P. And with some concentration bound, so if n is large, then the probability that this is close to this is high. So imagine the situation that you flip a coin. If you flip a coin n times, what's the probability that you get the number of heads is roughly 1 plus minus epsilon times n over 2. Say here, let epsilon be 0.1. What's the probability that you get 45% to 55%, of them exactly had? As n grows large, it's intuitive that such probability goes higher. We didn't actually learn the necessary, background to actually show that, but intuitively it's clear that the vertices must have a degree very close to its expectation if n is large. And this is called concentration. And we define some random variable, and then we show that the probability that this random variable is very close to its expectation is, the probability is very high. Then, with high probability, all those random variables is very concentrated around its expectation. We call that concentration or concentration inequality, such as Cherenkov inequality or Azuma's inequality. Anyway, by using that, we can actually show that with high probability, we have the maximum degree is at most say 2 np, which is 6 times n to the 3 over 4 times log n to the 1/4. Then what do we get? N over 2 is at least, say, some constant times, say 1 over 100 times 6n to the 3 over 4 times log n. Let's not write this way. Delta of g to the 4/3 over log delta of g to the 1/3. So this shows that there exists a graph whose acyclic chromatic number is at least some constant times the maximum degree to the 4 over 3 over some polylog term. So this roughly determines the asymptotic of the, worst asymptotic of the acyclic chromatic number in terms of maximum degree. So next time we will consider about the bounds on star chromatic number. Thank you.